This is a fluorescence-polarization-tag assay. It was developed by Dr. Stephen Withers at the University of British Columbia. It might be the catalyst to solving the antibiotic resistance crisis. Right now, this machine is testing different molecules to find the one that might be the next big drug.
My colleague in Guelph approached me. He had just discovered this class of enzymes, which they had showed were essential to the survival of a particularly nasty, pathogenic, dangerous organism.
This dangerous organism is, of course, bad bacteria, not the kind you find in yogurt. The newly discovered enzyme is a glycosyltransferase, also known as the GT enzyme. The GT enzyme is a class of proteins that transfers sugars to other molecules. They play an essential role in bacterial cell function. This makes bacterial GTs the perfect target for drug therapies.
The longer-term idea is that if we can discover very selective inhibitors of that enzyme, those inhibitors could be useful as antibiotics to stop that bacterium from surviving.
This machine runs a test that is cheaper and more efficient. It's a huge step forward from traditional methods, which Withers explained had several limitations.
They weren't appropriate for this enzyme because there were lots of limitations in them. And they were quite expensive to perform, so what we were trying to do was to get an assay that we can perform that doesn't cost as much. And that's important because ultimately it's not in the paper, but we've screened a library of 140,000 compounds. Now, if we can reduce the cost of that 10 or 100-fold, that's a lot of money to save. I mean, we just couldn't do it otherwise, so we had to bring the costs down. So our assay that we've developed allowed us to do the whole screen for about $20,000, as opposed to like 200,000.
Normal light consists of waves that vibrate in all directions. Plain polarized light vibrates in only one direction. All unwanted light waves are filtered out using something like a Polaroid lens.
So what's happening there is that you're selecting out light that's plain polarized in a certain fashion through passing it through the Polaroid lens. Now, so if you take this plain polarized light and use that to excite a molecule in solution so that it emits fluorescence, then the fluorescence that it will emit immediately after excitation will have the same polarization as the light that was added, that it was used to excite it. You could measure the reaction rate by measuring the polarization of the light that had been attached to that molecule. The polarization after a certain amount of time had been allowed to elapse for this molecule to tumble.
Tumbling causes the molecule to lose its polarization and emit light in all directions. Small molecules, such as sugars, tumble faster and emit light in all directions. This light is not plane polarized and cannot be detected. Large molecules, such as proteins, tumble slower and emit plane polarized light.
What that means is you don't have to do any washing of the cells or anything like that, because any molecule that has not been attached to a protein will just be tumbling rapidly and its signal is lost. But any molecule that has been attached to a protein, you can still measure the signal after a certain time has elapsed.
The only problem now is that the specific GT enzyme from this assay transfers a donor sugar to an acceptor sugar, not a protein. Therefore, there is no way of knowing if the transfer had actually occurred because the signal was lost. Luckily, Dr. Withers' postdoctoral fellow Zhuzhong Gao came up with a clever solution. He recalled the biotin-avidin association system. A biotin is a vitamin, a small molecule that binds very strongly to the protein avidin. They attached biotin to the acceptor sugar and performed the assay in a solution with avidin.
You've got this sugar now bound to this macromolecule and it's tumbling fully slowly in solution.
In the presence of an inhibitor, the donor sugar can't bind to the acceptor sugar. This is because the inhibitor has stolen its place. The fluorescence polarization signal is quickly lost. A successful inhibitor has been found.
And that becomes quite universal then, as long as you can attach avidin to your acceptor sugar, you can use this for anything.